Okay, so we are starting the next chapter, chapter 4, and this section involves normal subgroups. So in this first exercise, we are given two subgroups of a given group, and that given group is the general linear group of 2 by 2 non-singular matrices with real entries. And we have to say that whether each of these subsets is a normal subgroup of this group. So let's see. The first one, that is H, is the set of all matrices in our original group having rational determinant. Okay, so let us deal with that first. The first thing we notice is that the 2 by 2 identity matrix is an element in H. That's because it is first of all an element in the general linear group. That's because it has determinant 1, which is a non-zero real number. And the second thing is that determinant 1 is actually also a rational number. So by the definition of this set H, the 2 by 2 identity matrix belongs to H. Since, so this is part 1. Since the determinant of the element in our group is 1, which belongs to the set of rational numbers, this belongs to H. If you want, you can use round brackets to enclose the entries of a matrix. I like to use square brackets. So this proves that H is a non-empty subset of GL to R. Now we can proceed to show or see whether H is a subgroup or not. So that means we are going to use the subgroup test. We are going to consider two matrices in H and see whether their product belongs to H, and also see whether their inverses, that is the inverse of any one of them, belongs to H or not. So that is the first job. If we manage to show that that is the case, then H would be a subgroup of GL to R, and then the normality of H will come. So the next thing is this: let A and B belong to H. Then the determinant of A and the determinant of B are rational numbers. Note that we already know that since A and B are, after all, non-singular matrices, their determinants are non-zero real numbers. That is already known. But now, specifically, also the determinants are rational numbers. So, determinant of the product AB, which we already know is the product of the determinants of A and B, is also going to be a rational number, and that's why AB would belong to H. But again, that fact is already there in the background, that since these two determinants are, after all, non-zero, so the product of them is also non-zero. But we do not need to mention that here. We just simply write that this belongs to the system of rational numbers. Hence, the product AB belongs to H. We already know that AB belongs to this group because after all it's a group. So that is why AB belongs to the general linear group and its determinant is a rational number, so that's why it belongs to H. Also, what is the determinant of A inverse? This also we know, it is just simply the reciprocal of the determinant of A. And since this is a non-zero rational number, so its reciprocal is also, first of all it exists, and the second thing is that it is also a non-zero rational number. Hence, A inverse also belongs to H. Thus, H is a subgroup of the general linear group. Okay, now next comes the normal. Oh, I was trying to save this one. No, anyway I have to erase it. The second one, of course, is the set of all diagonal matrices in the general linear group. We will remember it. Okay. Now for showing that it is normal, let C be any element in our original group. That means C is any non-singular real 2 by 2 matrix. Now we don't really know whether the determinant of C is going to be rational or not, and it does not matter. All we know is that the determinant of C is a non-zero real number. Okay, then we know that C inverse AC, for example, where A of course is this A, belongs to our group such that, now in order to show that this belongs to H, of course we have to see whether its determinant, the determinant of this product, is a rational number or not. So we calculate its determinant, C inverse AC. This is going to be equal to I'm trying to be extra careful to clean the board so that I don't make a mess. Yeah, that's okay. So the determinant of this product is going to be, first of all, equal to the product of the individual determinants and where this one is going to be the reciprocal of the determinant of C. And this 2 of course is going to give us 1. That means we will be left with the determinant of A, which we know is a rational number. So after all, this determinant is nothing but the determinant of A itself, which is rational. Hence, C inverse A C belongs to H. So H is actually normal in our group. H is normal in the general linear group. Okay, next comes in part 2 the set of all diagonal matrices. Now note that the question asks us to ascertain whether this set, just like H, is a normal subgroup or not. So actually it will not be, and the normality will be violated. So there is actually no need to show that even it's a subgroup, or even we do not have any need to know whether the set of diagonal matrices forms a subgroup of the general linear group or not. We just show that the normality condition is violated, and that's just it. If it turns out to be a subgroup, it will not be normal. So that's it. And if it is not a subgroup, then that's it. That's where the story ends. So what we want to show is that we will take a diagonal matrix. It should be non-singular, of course. It should come from here, and also we are going to take two other matrices coming from this group and form this kind of product, and the product will not be a diagonal matrix. So that's what we are trying to show now. Note that this matrix, for example, 1 0 minus 1 1 is in our general linear group, and is it really? You see what its determinant is, 1 times 1 minus 0 times minus 1, that means 1, which is non-zero. So yes, it's a non-singular matrix. And say 1 0 0 2, this is a diagonal matrix. Oh, we haven't given any name to this set, no? Note that this belongs to this, and this, let us just write like this. This is a diagonal matrix in our group, that we need to mention. In this. Now, what will happen if we form this product? 1 0 minus 1 1 inverse times 1 0 0 2 times 1 0 minus 1 1. Now the inverse of this, its determinant is 1. So if we interchange this to, actually nothing is going to happen. If we divide by the determinant, then also nothing is going to happen. And okay, but in the off diagonal elements we have to multiply by minus 1. So that means 1 0 1 1. Okay, let me really verify whether this is the inverse of this matrix or not. If we multiply this one and this one, what do we get? If we multiply the first row and first column, say 1 times 1, 1 plus 0 times minus 1, that means 1. Okay. First row, second column, 0 plus 0, so 0. Okay. Second row, first column, 1 minus 1, 0. Okay. And second row, second column, 0 plus 1, 1. Yes, it is the inverse. And let us now multiply these two up. 1 times 1 is 1 plus 0 times minus 1, that means 1. 0 plus 0, 0. 0 minus 2, minus 2. And 0 plus 2, 2. Let me check once more. 1 plus 0, 0, 0 plus 0, 0, 0, minus 2, 2, minus 2, 0 plus 2, okay. And now this is equal to 1 plus 0, 1, 0 plus 0, 0, okay, this one is 0, 1 minus 2 is minus 1, yes, it will not be diagonal. And finally, 1 times 0 is 0, plus 1 times 2 is 2. Now this is, let's continue the sentence like this, is a matrix in our group. It will be in our group, no doubt, because that is why it's a group. That is not a diagonal matrix. So the set of all diagonal matrices is not a normal subgroup of GL2R. In our group, is not a normal subgroup of the group. Okay, so that's how the solution ends. But before we leave the solution, let me once more see. This matrix, of course, is a non-singular one. This one is also non-singular. Okay. So let's now see the next one. Find every normal subgroup of S3. Every normal subgroup of the symmetric group of degree 3. So we need to recall all the elements of S3. That's the first thing we have to do, and then we will see what the subgroups of S3 are, all subgroups in fact, and then we will decide which one of them are normal and which ones are not. We know, or rather I should okay, instead of writing we know, let me write we have. S3 equal to So we are going to have to use those notations for the permutations. These are the 6 permutations that we have. You remember this notation which represents that function from the set consisting of 1, 2 and 3 to itself, which sends 1 to 1, 2 to 2 and 3 to 3. That means it's the identity function. So just like that's what the notation means or represents. Then we have this function which interchanges 1 and 2 and fixes 3. Then I do have space here, so let me write 2 more here. And then we have the function which interchanges 1 and 3 but fixes 2. And then the other one which interchanges 2 and 3 but fixes 1. And then we will have 2 more permutations which do not fix any symbol. They change all the 3, 1, 2 and 3, all of them. This one sends 1 to 2, 2 to 3 and 3 to 1. And there is one more, it sends 1 to 3, 3 to 2 and 2 to 1. You can see that they are all different, 1 to 3, then 2 1 3, or you can see it systematically like this: 1 2 3 1 3 2, 2 1 3 2 3 1, 3 1 2 3 2 1. So these are all the elements in S3. And now we are going to write all the subgroups. The subgroups means all the subgroups of S3 are given like this. In order to make it more readable, I am going to write the subgroups like this, in this fashion. The first one is the trivial group. Let me call it H1. It is just simply the one which consists of the identity element, identity permutation. And it's a cyclic group. Let's just note that fact also. Then H2. H2 is the subgroup, cyclic subgroup generated by this element, this permutation, the second one. So accordingly, let me write like that. First, let me write the notation and then I will write what all its elements are. 2 1 3. The cyclic subgroup generated by this permutation, and this will have the identity element. Of course, it's always going to be there in every subgroup, and the only other element is going to be this. Why? That is because the order of this element in the group S3 is 2. So it generates a 2-order cyclic subgroup. Shall I have space to write the others like this? I have to be a little careful. I have to get it done in this part itself. So let me keep the elements for now. Let me write the next one. So this is going to be This one we have considered. Next, consider this one, the cyclic subgroup generated by this one, 3, 2, 1, and it also would consist of 2 permutations, the identity and this one itself. I think I will have to abandon this format of writing. 1, 2, 3, 3, 2, 1, and then H4. H4 is the cyclic subgroup generated by the next one. 1, 2, 3, 1, 3, 2, and this one also will have the identity permutation and just the generator. And then there are 2 more. The next one is H5, and it's also a cyclic subgroup. It is generated by this one or this one. If you consider the cyclic subgroup generated by this one and also the cyclic subgroup generated by this one, they turn out to be the same. Okay, and this subgroup has 3 elements: the identity element, this permutation, and this permutation. So let us write the things accordingly. 1, 2, 3, 1, 2, 3, 2, 3, 1, and 1, 2, 3, 3, 1, 2. And let us not forget that there is one more subgroup, which is S3 itself. Looking at these subgroups, you see one peculiar thing, that except the entire group S3, every other subgroup is a cyclic group, not just abelian but a cyclic group. Comma S3. Okay, so that means we have found how many subgroups? 6 subgroups. Oh, and in order to verify that these are the only subgroups of S3, because that question also comes, no? Well, right now you will just have to somehow, we already have come across Lagrange's theorem, right? I am forgetting things. In the previous chapter we have seen cosets and Lagrange. Okay, yes, we have Lagrange's theorem at our disposal. So that means we can take the help of Lagrange's theorem to ascertain that these are the only subgroups of S3. How? Because you know that the order of S3 is 6. So by Lagrange's theorem, whatever subgroup S3 has must have order that's a divisor of 6. That means the subgroups must have these possible orders. So you do not have to, for example, worry about any 4-element subset forming a subgroup. So such things will not exist. For this order, of course, there will be only one subgroup, which is the trivial group H1. And also for the order 6, we have only the entire group. And for these 2 orders, we have considered all the possibilities. Why are they all the possibilities? That part I leave to you. Okay, it will not be very difficult to argue why that is the case. Why? We have only 3 subgroups of order 2, H2, H3 and H4 and only one subgroup of order 3 which is H5. That part I leave to you. Okay, now we are going to decide which one from these are normal. The subgroups H1 and S3, that means the trivial ones which always are there in every group, are of course normal, trivially. The entire group and the trivial group consisting of only the identity element, they are always normal in any group. So here also they are normal. The subgroup H5 is normal because its index in S3 is 2, and a result that you find in this section, in the first section of the current chapter, tells us that in any group, if we find a subgroup whose index is 2, then it is going to be normal. And why is the index 2? That's because the entire group has 6 elements, whereas the subgroup H5 has 3 elements. 6 divided by 3 is 2, that's why. Because the index of H5 in S3 is 2. Okay, and the next thing we are going to argue is that none of the other subgroups is normal. That is, H2, H3 and H4 are not normal. And for that, we are going to form that kind of a product. Say you take one element of H2. There is no point considering this element, of course. You are going to take this element of H2 from H2 and some other element from S3 and form the product. That other element inverse times this times that other element, and that is not going to be inside H2. So that would prove that H2 is not normal. Similarly, H3 will not be normal and H4 will not be normal. So let's see one such calculation now. Okay. Note that okay, so I need space for doing that. Which one shall we take? Let me take the generator of H3, that is 1, 2, 3, 3 to 1, take its inverse, with that multiply the generator of H2, because this is H2, the generator of H2, 1, 2, 3, 2, 1, 3, and then this element itself, 1, 2, 3, 3 to 1. Let's calculate this product. Because this is a generator of H3 and H3 has order, we already know that this is an element in S3 whose own order in S3 is 2. In other words, the element is its own inverse. So that's why we just simply have 1, 2, 3, 3 to 1. Now let's calculate this product. Carefully recall that the calculation starts from the right side. 1 goes to 3, 3 goes to 3, so 1 goes to 3, 2 to 2, 2 to 1, so 2 to 1, so this one will be 2, but still let's see, 3 to 1, 1 to 2, so 3 to 2, and just like that, next this product, 1 to 3, 1 to 3, 3 to 1, that means 1 is unchanged, 1 goes to 1, 2 goes to 1, 1 goes to 3, so 2 goes to 3, so this one will be 2, 3 to 2, 2 to 2, yes, and note that we do not have it here, it is 1 3 2, we do not have any 1 3 2 here, so this does not belong to H2, hence H2 is not normal in S3. Hence, or shall we conclude finally? Let's go through the other calculations as well. Next, we want to show that H3 is not normal. So let's now switch the roles of this element and this element, because this is the generator of H3. So now what we are going to calculate, 1 to 3, 2 1 3, inverse 1 to 3, 3 to 1, and then 1 to 3, 2 1 3. Okay, so this one also, since this is an element of order 2, its inverse is the element itself, 1 to 3, 2 1 3, and then this product, what will it be, 1 goes to 2, 2 goes to 2, so 1 to 2, 2 to 1, 1 to 3, 2 to 3, 3 to 3, 3 to 1, 3 to 1. Then this product, 1 to 2, 2 to 1, so 1 to 1, 2 to 3, 3 to 3, 2 to 3, 3 to 1, 1 to 2, 2. Does it belong to H3? 1 3 2? No, we do not have any 1 3 2 here, so this does not belong to H3. This does not belong to H3. Next, we consider the case of H4. The generator of H4 is this. In fact, this final result actually belongs to H4, but that does not give us normality. And what shall we choose for this element? Let's choose this one itself. 1 2 3, 2 1 3. Inverse, so this is the, no, I should not make any mistake, this is the generator of H4, 1 3 2, because it fixes what? The elements in H5 except the identity element, they do not fix any symbol, but this one is the generator of H4, 1 2 3, 1 3 2, and then on this side 1 2 3 2 1 3. Okay, now I can get rid of this line, or can I? Let me do the calculation here itself, and then we will have to see whether the final result belongs to it or not. 1 2 3, 2 1 3, just like before. And what about this product? 1 2 3, 1 to 2, 2 to 3, so 1 to 3, 2 to 1, 1 to 1, so 2 to 1. So this one will be 2, but still let's see. 3 to 3, 3 to 2, yes. And finally, this product is what? 1 to 3, 3 to 3. So 1 to 3. 2 to 1, 1 to 2, 2 to 2, and 3 to 2, 2 to 1, 3 to 1. Do we have any 3 to 1 here? No. So that means this does not belong to H4. H5 we do not need because already we know it's normal. This does not belong to H4, or does not belong to. Here also I should have written, okay. Hence, H2, H3 and H4 are not normal in S3. So 3 subgroups that are normal, the trivial group, S3 itself, and that 3 element subgroup, and 3 are non-normal, which are this H2, H3 and H4. So that is the solution. Next, if N is the normal subgroup of G, and N has 2 elements, show that N is a subgroup of the center of G. Out of those 2 elements, one of them of course is the identity, but there is one more element which of course will have to be an element of order 2. So it's like one of these subgroups, H2, H3, H4. It should be cyclic. However, unlike the case of S3, note that here G need not be finite. Only N is finite and it has order 2. But we do not need G to be finite. Although it's not related to the solution, can we think of an example of an infinite group in which you find a 2-order subgroup which is normal? How about the group of non-zero real numbers under multiplication? That is a group and it's abelian also, so actually any subgroup will be normal. In it, you can consider this 2 element set. Just one glance at the set tells us that this set is closed under multiplication of real numbers. So by the one of the subgroup tests, it will be a subgroup of this group, and because the group is abelian, so it will be normal. So it can happen. In an infinite group also you can have a finite normal subgroup having two elements. But anyway, let's now see the solution. Let, because n has order 2, it will have two elements where E is the identity and A is not E, that is understood. Okay. Also, let G be any element in G. Okay. We of course have G inverse EG, which is equal to E in N. Oh, what? Okay, why the hell did I write this? I am not going to show that n is normal. N is given to be normal. I have to show that n is contained in the center of G. Okay. Instead, this is what I should have written. We of course have G equal to EG, because the identity element commutes with every group element. Also, normality of n gives us this thing: G inverse AG belongs to n, because A is coming from n, so this element due to the normality of n should again be in n. Now if so, being in n, this will either be E or A. Now if G inverse AG is equal to E, say, then using the elementary cancellation laws, you can understand, you can write this as G inverse EG, and then you can cancel G inverse and G from both sides in order to conclude A is equal to E. Then A is equal to E, which is not possible. So we must have G inverse AG equal to A. Now you multiply on both sides from the left by G and use the group class to conclude that AG is equal to GA. Which gives us AG is equal to GA. So what have we shown? We have shown that E commutes with any group element, also A commutes with any group element. That means all the elements of N commute with all the elements of G. So all the elements of N are central elements. Thus, we are just simply going to write the final conclusion. So that is the solution. Next, let n be a normal subgroup of, again a normal subgroup is given, okay. Let n be a normal subgroup of G. Let H be the set of all elements H of G such that Hn is equal to Nh for all n belonging to n. I don't understand the need to always write things like this in words when we have notation for sets, because if we use mathematical notation it becomes compact, but that's how it's given here. Show that H is a normal subgroup of G. So we have two parts. First we have to show that H is a subgroup of G, and then we have to show that H is normal in G. So let's go through the subgroup part first. Since En is equal to Ne for all, but before we continue writing the solution, let us once more see what H actually is, because see, this is the problem I was mentioning back there. If you write things in words like this, of course we can understand when we read the sentence, but when we use a mathematical notation, we can see at once what the set is. Anyway, so H is the set of those elements of G that commute with all the elements of N. Okay. And we already know that the identity element from G commutes with all the elements of N. Actually, it commutes with all the elements, but in particular, all the elements of our normal subgroup also. For all N, we have E belonging to H. So now we know that H is a non-empty subset of G. So now we can start verifying that H is a subgroup of G. Let this non-emptiness must never be forgotten. Okay, we have to first of all make sure that it's non-empty and then do the rest. Now let us consider two elements h1 and h2 in H. Okay, then for all elements n belonging to n, let's go through the calculation. h1 h2 n, by the associative law, this is equal to h1 h2 n. Because h2 is coming from h and n is coming from n, h2 and n are going to commute with each other, so we can switch the order and write in place of h2n nh2. Then you use the associative law once more and have this. But h1 also comes from capital H, so it will also commute with n. So this is nh1 h2, and then you use associativity one final time to have this. So you look at the first term and the last term in this series of equalities. h1 h2 commutes with n, which is an arbitrary element of capital N. So h1 h2 by definition of capital H belongs to H. Hence the next thing we have to see is that the inverses also belong to H. So for example, we are going to now consider whether H1 inverse also commutes with all the elements of N. Also, h1n equal to nh1, and that n is still this arbitrary element from capital N. Okay, so h1 already commutes with n, and we can now conclude something from here. If we multiply on both sides from the right by h1 inverse, what do we get? h1n h1 inverse is equal to n, because that h1 inverse will vanish. And now you multiply on both sides again by h1 inverse but from the left, then this h1 will vanish, because h1 inverse h1 gives you the identity, and you are going to get this. So that means just like h1 inverse also commutes with n. Hence this belongs to H. Thus H is a subgroup of G. Okay, and now we come to the normality part. To prove that H is normal in G, let us consider H in H and G in G, and let us first write what we need to prove, okay, and then see what we can where we can get from there. note that what is it that we need to show? We need to show this G inverse Hg belongs to H. This is what we need to show. And this means what? This means, so that's why I am giving double implication, because it's equivalent to, its meaning is this: G inverse Hg n is equal to n G inverse Hg for all n. Oh, I started writing that in. I have got this habit. For all n belonging to our normal subgroup. Okay, now we try to change this equation to some equivalent form. Now this can be next. What can we do from here? Let's see. So what we are going to do, I mean, we need to reach some equivalent form of this equation which we somehow know is true, so that from there we can come back and have this as a consequence. That's why we have kept the possibility of going in both the directions. And we have to also make sure that every step you write is actually equivalent to the previous one. This is equivalent to this because this is what it means. Okay, next. But now the question is, where can we go from here? Okay, let me bring all the things on the right side to the left side except H. I'm going to keep H on this side and let's see what happens. So what shall I get? If I bring n to this side, I'm going to get n inverse. I think it will be better if I do it in steps. N inverse G inverse Hg. Due to the general associative law, there is no need to write any bracket. This is equal to G inverse Hg for all n in n. Unfortunately, we have to actually keep on writing that for all n in n. If you want, you can use the logical symbol for this for all quantifier, which looks like a V with a horizontal bar. We, however, write like this. Yeah, now it will be easier to bring G inverse and G on this side. So if I multiply on both sides by G from the left, I get G n inverse G inverse H Gn, and also I am going to multiply on both sides by G inverse from the right. So G inverse, and now I will have only H on the right side. Okay. Now what? Now if one looks carefully, this part, if I want, I can put brackets here. I can use brackets or not use brackets, it does not matter. Is this element within these brackets the inverse of this element? It is. Why? How? This is how. This is just G and G inverse whole inverse H G and G inverse is equal to H for all n belonging to n. Okay, so the question of this being the inverse. Okay, now when you take the inverse of this, you are going to take the inverse of each factor in this product. If I want to say it like that, you have to take, while taking the inverse of this product G and G inverse, you have to take inverse of G, that means G inverse, N inverse and inverse of G inverse, but the order will be reversed. First the inverse of G inverse will come, which we have here, and then the inverse of N, and then the inverse of G. That's why we have like this. Okay, so that means whatever this statement means, this one also means the same thing. That means showing this is equivalent to showing this. Now is this true? That is the question. It is true, and that comes from the fact that n is normal in G. Now, since n is normal in G, G and G inverse belongs to n for all n belonging to n. For all n belonging to n. If this looks slightly wrong to you, because in the actual condition for normality that you have in that theorem or proposition, I forgot what that is, you have inverse here and the ordinary element here, but note that G and G inverse is actually again in that form only. So you do have an inverse first and then an element of n and then the element of whose inverse you are considering here. Okay. Now since n is normal in G, this belongs to n for all n belonging to n. But we are considering H from where? H we have considered from H, capital H, and the definition of capital H is that it is the set of all elements that commute with all the elements of n. So H will also in particular commute with these elements. Since H belongs to H, we have, so commutes means what? I do not want to get the order wrong. H times G and G inverse. H commutes with this element. G and G inverse H. We continue this for all, okay, in order to be absolutely precise about what we are doing. And that itself is equivalent to what? Okay, now you multiply on both sides of this equation by the inverse of this G and G inverse from the left side, so that this one vanishes and you are left with this G and G inverse H. G and G inverse is equal to H. So that means whatever we had to show that H is normal in G, that condition G inverse Hg belongs to H, we came to know that that is equivalent to showing this, and here you have shown this. So that's it. Hence H is normal in G. There are better ways of tackling this particular exercise, but it is best to first of all work with elements, and then only as we gain more and more experience with these structures, we can work with collections of elements at once. Okay, that will come afterwards. First, it's better to get our hands dirty and calculate like this and see what is really happening with the elements. And that's just it. So I end the video here itself tonight. And tomorrow we are of course going to continue with our analysis, where we are right now in the middle of the proof of Fubini's theorem. So tomorrow we are going to see a big chunk of that proof. So with that, I am going to wrap things up. So see you tomorrow with Fubini's theorem proof, a part of it, a little more. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.